Hi, this is Cheryl Resch, and in this video, I'm going to go over my buffer overflow assignment. So this is the assignment here on the left in this Word document. And here I'm running my emulator. And we have a file called main.c that we're going to compile and run with the debugger. So let's look at main.c and see what it does. So this was inspired by a program I found from Security Nick. Thank you for that. First thing we're going to find is a function called arbitrary code, which doesn't do much of anything, just prints some things. And then we have a function called getInput that allocates 8 bytes of space for a variable called buffer, and then uses getS to read in that buffer, which is our function that is vulnerable to buffer overflow. And then putS is going to print that buffer. Then I have a function called benign function. I put that in there just to get a little more context about stack frames. And then main. And we'll see that main calls benign function and get input. We did not call arbitrary code, but what we're going to demonstrate is if we can look at what the address in memory of this instruction is, we can overwrite a register value. We can make it so a register gets written with this address, and the program will jump to this instruction and run it. So we'll show how that can happen. So let's compile this thing. So we're going to use the GNU compiler. Our output file executable is going to be called main. And we're compiling main.c, and we want to use the debugger, so the -g. And it says, don't use getS. That's dangerous. Don't use it. Please don't use it. And yes, you should not. It is dangerous and should not be used. We're using it today to show how dangerous it is. But in general, you shouldn't run it. You shouldn't use it. So let's run gdb main. So we're in the debugger now. Set some breakpoints. Okay. And then we're going to run disassemble main. And we're going to look at, so this is the ARM assembly code. This is main function was translated into this ARM assembly code. And we're going to have a look at this for a minute. So what's the first thing that happens? This is store a pair of registers. So we're storing a pair of registers x29 and x30, and this is saying store this 32 bytes below the stack. So make me a stack frame that's 32 bytes and put these 2 registers in there. Now, why do we do that? So both of these registers are pertinent to the procedure currently running. So x29 is the boundary of the stack frame for this procedure. It's called the frame pointer. And x30 is the address of the instruction you need to run when you're done with this procedure. So it's called the return address. So when you return from a function, you're going to run the next instruction after the one that called this function. So you need to know where to go back to. But what happens when you run a nested procedure, another procedure with a branch and link calls a procedure, these 2 things are going to get overwritten with new values pertinent to calling benign function. And we need to get these things back because we need to know how big our stack frame is, what the boundary of the stack frame is, and we need to know what address to return to. So we put them on the stack in memory. When benign function is called, x30 is going to actually be overwritten with this 914 address. So we put it on the stack, and right before we return, we get it out of memory and put it back into x30. And actually, this is one of the things we're going to take advantage of, is the ability with this vulnerability to overwrite memory in the stack and end up putting something back into x30 that has been corrupted. Yeah. So, but we save it because on a new procedure call, these will be overwritten. So we need to get them back. So we put them on the stack. So let's run. Now we're inside of benign function. And we're going to look at the register value. So we hit enter because the ones we're interested in are at the bottom. So we want to know, so again, x29 is that frame pointer. Here's our return address as predicted. It has that 914 on the end. The zeros have turned into A's. That's an address translation, virtual memory thing, a lesson for another day. So that would go in here. And then here's our stack pointer. So the boundaries of our current stack frame are going to be, this is the boundaries of our current stack frame, right? So there we go. We're going to have hit N and type return 4 times to get to return Z. Now we're in the benign function. We have 2 stack frames on the stack. So we have the main stack frame, and up on top of that, the benign function stack frame. So let's look at stack memory. So this is saying, show me 6, this is examine memory, show me 6 8-byte chunks of memory starting at the address of the stack pointer. So remember we said that x20 to x40 are the bounds of the current stack frame. So this is the top of the stack. And then the other boundary of benign function stack frame is B40, right? So that's 16 bytes. So this is the 16 bytes of benign function stack frame. And then below that is going to be main stack frame. Because again, as you do nested procedures, stack frames get stacked on top. So this is the one for main, and this is the one for benign function. Okay, so now I'm asking students here to copy all of this into this table. I'm not going to do that, but you know, the students are being asked to do that. We can just look at it right here. So again, here's a drawing of those stack frames. So remember, we had that first is the main stack frame and benign stack frame is on top. So thinking about what's in table 1. So in table 1, the current bounds of the current stack frame, right? Thinking about those values, what are A and B? So A is the top of the stack, right? This is the stack. A is the top. So A is going to be the stack pointer. That's the address pointed to by A. B is going to be the current frame pointer because that's the boundary of the benign function stack frame. And now, given this information, use the values you entered into table 2, which is shown right here. What are the values of x29 and x30 that were written early in the execution? So when we looked at disassembled main, we saw that x29 and x30 were saved. So where are these values? And we talked about, this is that main stack frame right here. So this is going to be x29. It's going to be a value that's near, you know, around the same value as the stack pointer because it's in stack memory, right? So it's, looks like it's 64 bytes away. And then x30 is going to be that other value because we saw with that store pair that's what that was x29 and x30. So that's x30. And then using this information, what is the address pointed to by C in figure 2? Well, stack pointer, frame pointer, this is going to be main's frame pointer, right? That's the old frame pointer because the boundaries of main stack frame ends at its frame pointer, right? So C is going to be that main stack pointer. Frame pointer, sorry. All right, so let's type N repeatedly until we get to get input. And here we're just looking at, again, just copy these register values into here just to show we're in a new function and the values have changed. It's a bit confusing that the x29 and x30 are the same. So it actually hasn't moved the stack pointer. That's a little strange, but that's okay. And now we're going to type n repeatedly until the program is waiting for input. So the cursor is all the way on the left. And we're going to type in the first 8 characters of our name. So everyone has different value here. So students can't all turn in the same thing. They have to actually get this far on their own. There's a couple places where I ask for screenshots. But anyway, so I'm typing my name. And now I'm going to look at the stack again and see what's there. And that's kind of cool. Stuff has changed a bit, but one thing I see a frame pointer, and I see a return address. We're going to copy all of this again, copy these 9 values into here. But this one's interesting. This is that buffer that I typed in. This is that buffer variable. Because look, it's little endian and it's backwards, but here A is 40, capital A is 42. So here's a capital C and an H, an E. Why my cursor's decided to not be cooperative. But anyway, so here's my buffer variable. That's kind of cool. All right, so we're going to copy all of those. And then here we're saying, what does the data in the top in memory shown in the top row represent? And we can see that it's a frame pointer and a return address because those are familiar looking. And we know that 91C is the return address from when get input was called, because we can go all the way back to our here. When get input is called, 91C is that return address. So it was saved to the stack when it is the x29 and x30 saved to the stack when get s was called, because that's get input's return address. And then again, circle or highlight the buffer variable. There it is. So it's like, oh, look, I can see my variable. It got put on the stack. So let's hit N enough times to complete execution. Yeah, so we're done. And now we're going to run this thing again. And we're going to keep going until it's waiting for input. There we are. We're going to type something that is at least 18 characters long. So there's 1, 2, 3, 4, 6, 7, 8, 9, 10, 6, 7, 18. Okay. And then we're going to type in, and we're going to look at our stack memory. And zounds, look at all those A's. So this was our variable. Hey, this used to be our main stack frame. What happened to it? So we're going to fill in this table again with these 9 values go into this table. But what happened to our stack frame? It got overwritten. That all those A's I typed in overwrote this frame pointer and return address. Zounds. What's it doing? Overwriting stuff that it has nothing to do with even this stack frame. It's overwriting the main stack frame. So we're going to type N repeatedly until we get some question marks. And that question mark is actually like, this is supposed to be the address I'm returning to, and this is not computing for me. So it's saying, what is going on? So let's look at the registers. And well, that's a problem. Look at our frame pointer got overwritten. What happened was they got corrupted, right? So here's our return address. That's a problem. because the buffer was allowed to overflow and write adjacent memory, it corrupted our registers. So we're going to quit and quit. And then one of the things we're going to do is let's look at the address of this arbitrary function thing. And so the address we're interested in ends in 878. So we're going to keep that in mind. And then we're going to quit. And let's run our executable. And let's put in a really long input. And what happens? We get a stack overflow. We have our X29 overwritten with what looks like some wacky stuff. And we have a seg fault. Now we're going to see about this overwriting an address. Like, can we craft input so that this X30, which is actually called a link register here, can we stick an address in here? And what is good news is that most architectures now have protection against such things. And that protection is called ASLR, Address Space Layout Randomization, where you can't guess addresses anymore. It puts procedures into random places in memory so that mean people can't guess addresses. So we have to turn that off. But I'm asking students to research this and look up what it is, but we're turning it off. And then what we're going to do is we have crafted input. So this is piping input into main. So we have to pipe in this hex address. And so we're going to do that with this command because you can't really do it with typewritten. So we're going to type it in. And look, we have our arbitrary code running. Oh no. So we actually were able to overwrite X30 with the address of the first line of that arbitrary code function. And so now we're going to look at what happens if we turn ASLR back on, where actually we can't go away. We aren't allowed to know exact addresses of every instruction. And now when we try to do the same thing, we still have a seg fault. And actually you can see this is what's in X30, but now that instruction isn't exactly there. So at least this is a way of preventing buffer overflow vulnerabilities. Another way to prevent buffer overflow vulnerabilities is to actually write code that's not vulnerable. So here's another thing we can do is just not use getS. What the heck is going on? I'm so far in this, I'm going to leave this in because I'm so tired of takes. Anyway, let's fix this. There. I don't know what that was about. Nano is our friend. But let's put in a better one. So we're going to put in fgetS buffer 8 standard in. That's much better than using getS. And we're going to compile this. And we'll run main new. And we'll type Cheryl Resch is a nice person. And look, it just read 8 characters. Wonderful. The other thing I want students to do is to go to the Common Vulnerabilities and Exposures website. I thought I had it up. Yeah, there it is. And just learn more about vulnerabilities. So this is a database of all vulnerabilities to publicly available code. I like to teach them about this website and to show them that, look, buffer overflow is not a thing of the past. Oh no, it's actually the most dangerous vulnerability still, even though the first vulnerability was the first vulnerability, and it's still the most dangerous. So here's one just from a couple weeks ago, and this is a biggie. It's Google Chrome is vulnerable to a heap buffer overflow, which we did a stack, but still an out of bounds memory write via a crafted HTML page. And this is only a couple weeks old. Anyway, thank you for watching, and I hope you enjoyed the video, and I hope you enjoy the assignment.